In this video, I'm going to show a powerful technique to extract important information from an indicator. We will use the Relative Strength Index, or RSI, as an example. Later in the video, we will use a simple predictive model to build a trading strategy. The RSI is one of the most well-known technical indicators. It has a single parameter. I'll call it the period. I commonly see the RSI on the charts of discretionary traders when they post on Twitter or whatever, and I've seen the RSI used in a variety of ways. Some choose a short period of 2 or 3 to scalp small moves, others use a longer period to spot divergences or look for so-called overbought and oversold conditions. To be honest, I've never found any of these ideas terribly effective, but this video is not about any of those ideas. The point I'm trying to make is that the RSI is used by many traders in many different contexts, and various periods are used. Because of the broad attention this indicator receives from traders, it's possible that those traders create patterns in the broad behavior of the indicator, which we will attempt to capitalize on. Let's look at the behavior of the RSI across many period values. This is a script to visualize a few things about the RSI. First, we load in data from a CSV. This is hourly Bitcoin data. We define a set of period values for the RSI. I chose 2 up to and including 24. 2 is the minimum period value, and 24 seems like a reasonable max as we're using hourly data and there are 24 hours in a day. I'll use this set of periods for the remainder of the video. We create a data frame for all the RSIs, then loop through each period and compute the RSI using the pandas TA module. We plot the histograms, the RSIs, and the correlation between the RSIs. Here are the histograms for each RSI period. For most period values, the distribution is bell-shaped. The notable exception is the 2-period RSI. Sometimes traders will use the Fisher transform on the 2-period RSI to get a more bell-shaped distribution, but that's a story for another video. Here's a plot of all the RSIs together. This looks a bit confusing, but I want to show the RSIs all move together. Notice they all increase and decrease together, but by varying amounts depending on the period. Here is the correlation between the RSIs. They are heavily correlated across the period values. The most distant relationship is between the 2-period and 24-period RSI. It still has a 0.43 correlation, which is a fairly strong relationship. RSIs of different periods have a large amount of overlap in information. We have a total of 23 RSI periods, which is a high dimensionality, and because of the high overlap in information, we're going to use principal components analysis to reduce the dimensionality while preserving the maximum amount of information. Here's a simple example. This is the 24-period RSI and 12-period RSI plotted together in a scatter plot. There is a strong linear relationship between them. This red vector is on the axis with the most variance among these two variables. The red vector is the eigenvector associated with the highest eigenvalue. This blue vector is the other eigenvector. There isn't as much variance along this axis. Most of the information is along the axis of the red vector. This example is just 2 dimensions. We're going to do the same procedure using the 23 different RSI periods. We cannot visualize 23 dimensions, but conceptually it is the same. Let's look at the code for principal component analysis. We're going to start with a in-sample example. We will perform the principal component analysis with a rolling window later. We load in the data from a CSV and compute our RSIs. We subtract the mean value from the RSIs. This centers all the RSIs at 0. We drop the NaN values. We compute the covariance matrix of the RSIs. We find the eigenvalues and eigenvectors of the covariance matrix. Each eigenvalue is associated with an eigenvector. The larger the eigenvalue, the larger the variance along that axis or vector. We sort the eigenvalues in descending order, and then arrange the eigenvectors in the same order. Now we get the first 4 principal components. The number of components to use will be an adjustable parameter in the model we use later. Here, 4 is an arbitrary choice. To get the principal components, we find the dot product between the RSIs and the eigenvectors. I think it is interesting to plot the eigenvectors. These vector values are multiplied by the corresponding RSI period in the x-axis. The first 4 components pay little to no attention to the larger values of the RSI period, which isn't surprising as we saw the higher values of the period have the most intense correlation with each other. Anyways, let's use the principal components to build a prediction model. This script computes the model in sample. Before we look at the code for the model, let's look at the setup. We load in data from a CSV and compute the RSIs. We create a target variable. This is what the model predicts. I used the change in the log closing price over the next 6 candles. We'll consider other prediction horizons later. We drop the NaN values from the target and RSIs. Then we call this function PCA linear model, giving the RSIs, the target, and the number of components to use. Here is the function that creates the model. We subtract the means from the data and get our eigenvectors. We already saw this stuff. We get the specified number of principal components and add them to this data frame. The model is as simple as it gets, a least squares linear model. We call SciPy's least squares function to find the model coefficients. This least squares function returns some other stuff, but we only need the coefficients. That's why we have the 0 index on the end here. We get the model predictions in sample by getting the dot product of the principal components and the model coefficients. These next two lines, I get the 99% quantile and 1% quantile of the model predictions. These will serve as decision thresholds. Let me show you why. Here's a scatter plot. The model predictions are on the x-axis and the target is on the y-axis. These are in-sample predictions. I plotted a white line at 0 for the target. When the dots are above this line, the market went up over the next 6 candles, and vice versa. At first glance, it may look like our model failed. There isn't a clear relationship between the model predictions and the target, but let's look closely at the extreme values of the model predictions. When the model prediction is near its positive extreme, we can see that the market goes up more often than not. And similarly, when the model prediction is near its negative extreme, the market goes down more often than not. This phenomenon isn't exclusive to this model. It's present in almost every model and indicator. In market data, values at the extremes tend to have the most predictive power. This is why we get the 99% and 1% quantiles of the prediction. The 99% quantile serves as the threshold to take a long position, and the 1% quantile is the threshold for a short position. Let's walk forward this model to see if it works out of sample. This function implements the walk forward. We pass it the open high-low close data, a set of periods for the RSI, the train size, which is the number of candles we train the model with, the step size, the number of candles to wait between trainings, the number of principal components to use in a model, and the look ahead for the target variable. We compute the RSIs. We keep track of the next candle index that we will train at with this variable. We compute the target, the change in the log closing price over the specified number of candles. The outputs of the function are declared here. We have the model predictions, the thresholds, and the signal. We loop through each candle in the data. We check if it is time to train. If it is, we get the RSI values from the most recent train window. We subtract the look ahead from the current candle index to avoid cheating with any future data. We train the model with PCA linear model, which we already went over. Then we increase the next train variable by the step size. Now we compute the model prediction for the current candle. These are the out-of-sample predictions. We get the current row of RSI values and subtract the means. We compute the principal components using our eigenvectors. Then we get the current prediction by computing the dot product of the model coefficients and the principal components. We add the current prediction and thresholds to the output arrays. Then we check if the current prediction is above or below the thresholds. If it is above the upper threshold, we set the signal to 1 for a long, and if it is below the lower threshold, we set the signal to -1 for a short. After the loop, we make an output data frame. We apply a moving average to the signal with the specified look ahead. This is because when we predict, for example, 6 candles out, the idea is to take a position and hold it for 6 candles. But if the model prediction is above the threshold 2 candles in a row, then the positions overlap, meaning we take one position, then take another. By taking an average of the look ahead, we size the positions for the maximum amount of overlap. So with a look ahead of 6, if the model prediction is above the threshold, we take out a 1/6 long position. And if the prediction is above the threshold again the next bar, we increase the position to 2 out of 6, and so on. Here's the main section of the script. We call the walk forward model function. I again use 2 through 24 for the periods of the RSIs. I use 2 years as the training period, and 1 year for the step size. My first guess was using 3 components with a look ahead of 6. We get the strategy returns by multiplying the return signal by the next log return. Then we compute the profit factor. Here is the cumulative log return of this strategy, with a look ahead of 6 and 3 principal components. The profit factor is 1.53. The performance looks pretty good, but let's try a wide range of parameters to see if this model is robust. Here are the profit factors across several parameter combinations. It works on most combinations. Longer look-aheads have worse performance. Also, a higher number of components seems to perform worse as well. It appears the model is overfitting and therefore not generalizing out of sample when many components are used. The optimal number of components appears to be 2 or 3. Using a look-ahead of 1 candle has the best profit factors, but this test does not include slippage or trading fees. The shorter look-aheads will be more adversely affected by these, as a shorter hold period will result in a lower average trade. At a look-ahead of 1, the average trade could be less than the trading fees required to open and close a position. But overall, the model appears to be fairly robust. The RSI principal components can be used in whatever model you want, perhaps including other informative features. This model was just to show the concept. Computing the principal components of many similar indicator series with high correlation is a trick I've used for a while now. It can be applied to other indicators that have a lot of overlap, perhaps the ADX or some kind of volatility indicator. Principal component analysis is a great way to summarize a lot of information, reduce dimensionality, and ease the burden of selecting parameters for indicators. Another thing to note, I used the most basic form of principal component analysis. There are a ton of different techniques out there for other forms of component analysis, which of course will yield different results. The Python library scikit-learn has quite a few principal component techniques implemented if you want to experiment. If you like my videos and want to support the content, consider throwing me a few bucks on Patreon. Thank you to those who did become a Patreon. I appreciate it. Anyways, that's it for this one. Thank you for watching.